Okay, so we're going to continue with a single phase full wave uncontrolled rectifier again. So we're going to complete the session. So yesterday we did discuss on the single phase full wave uncontrolled rectifier with a resistive load, and then we move into resistive and inductive load, and then we also have the case of resistive inductive plus the back EMF. Okay, the back EMF. Right, so just to refresh what happens to the circuit operation. We look into the resistive load for the case of resistive load. So during positive half cycle, we're going to see that D1 and D2 uh, experience the forward bias, right? During positive half cycle, D1 and D2, the diagonal diodes here will be on because of a positive forward bias, and then we have the current flows in that directions, right? So D1 and D2 will be on, and D3, D4 during that time will be off. So and then we have the output voltage follow the supply voltage. So this is a full wave rectifier output voltage waveform. And then during the negative half cycles, so during the negative half cycles here, we're going to see that D1 and D2 now reverse bias, and D3, D4 are forward bias, and therefore the output voltage will be following the opposite to the supply voltage. So that's why this is what the full wave rectifier output voltage waveform will be. Right, and when we talk about the output currents, because this is a purely resistive load, the output the output current waveform will copy exactly as the input current, but copy the output voltage waveforms, but it's scaled down by a factor of R, because I equals to V divided by R. So it also have this pulse, okay. And if you reflect back to the input current, so the input current always carry the output current actually. So if I can mark here, so this is your input current, okay. So that input current actually carries the output current. So during positive half cycle, it will be equals to supply of the output current, and then during the negative half cycles, it will actually equals to the negative of the opposite to the output current here. So the input current also will be sinusoidal. But in the case of resistive and inductive load, and to discuss that, we're going to assume highly inductive load conditions. So when it is in the highly inductive load, we're going to remove and replace this R plus L with a constant current. Okay, so we're going to remove and replace. So this is the circuit that we're going to look at. So this is the circuit that we're going to focus at. So we have a constant current at the output. So therefore, if you look at this current, actually the output current will be a constant current I DC. So in that case, the input current will be square waveform, and we did discuss on how to get the harmonic or the Fourier series of the square waveform, square input current. Okay, so during that time, we also when we look into the I'm going to show you what happens during the cycles. So let me reduce. Okay, so this is also the simulation. This is simulation of the PCM simulation of the full wave rectifier with a constant current output. So IDC here is the output current, and IAC is the input current, the square waveform here, isn't it? Right? So in this case, when we look into the diode current, diode 1 and diode 3, okay, so diode 1, this is actually diode 1 here. This is your diode 1, and then we have diode 2 here, and we have diode 3 there, and then we also have this diode 4 here. Okay, so if you focus on the positive half cycle, during this time we're going to see that D1 and D2 is on, so that's why it carries the output current of IDC, and ID3 will be off. So this is your ID3, the current through your D3. So when it changed to the negative half cycles during this time, okay, when it's changed to the negative half cycle, if you look carefully, the current inside the ID1 and the ID2 change state, change levels instantaneously, which means it jumps from 0 to the IDC. And for the diode current, diode D1, it reduces or it falls from IDC to 0 instantaneously. Right, so that happens if we have a input, if you have a circuit with a purely with a resistive inductive load, with highly inductive load condition. Okay, so now we're going to look at what happens to the circuit if there is a LS, there is an inductance in the front end. What about if you have the source inductance in the front end? So this source inductance actually may come from the cable, and also it may come from the transformer, because we know that if you talk about the system, you always have three-phase supply from the TMB, and then it is stepped down, or there will be a step down to single phase rectifiers. 240 volts. So there is a transformer somewhere inside. So because of that transformer has a large winding, so it will be represented by a source, inductance source inductance, and also the cabling. So that's why in practical we always have this source inductance. So now we're going to discuss on how does it affect the operation of the circuits with if we have that source inductance in front end. So that would be in 4.3, 4.2 here, okay, in this section, right? So resistive and inductive is source inductance. So we're going to look at the circuit. So before that, okay, this is the intro. The effect of finite isolated circuit operation is also important, since in practical the source could be from the cable or transformer windings, right? So first we're going to analyze with a resistive load. So if it's a resistive load, a purely resistive load, it only affect the source inductance here, only affect the phase difference between the output voltage and the supply voltage. So the output voltage will be shifted or will be delayed or lagging behind the supply voltage by phi angle, and you can find the phi angles here by using this equation. It's just a matter of inverse tangent omega ls, the source inductance, divided by the resistive inductance, so the value of the resistance of the output purely resistive load. Okay, so that is mainly the effect of having that source inductance to the circuit. Okay, what interesting is when we look into the case of highly inductive load or with a resistive inductive load. Okay, so to focus on the effect of the source inductance, we're going to assume again a highly inductive case whereby the output here will be replaced by a constant current. Okay, so in this case we're going to replace, which means you're going to remove this, not put in the parallel, but we remove this and we're going to connect a constant current at the output. Okay, so we're going to connect the output current, the constant input current, output current with IDC in the front end, and we do have this source inductance. Okay, so before this, I've shown you without the source inductance, the current jump. Okay, so if you look into the ID1 and ID3, the current jump instantaneously without the source inductance. Is that it? Because it's purely resistive load, it jump from IDC to 0, and for the D3 from 0 to IDC instantaneously at this point. Okay, so now with the source inductance, let's have a look at the voltage waveform here. So if you observe, okay, during the effect of having that source in nothing, we got to see that the current, okay, let's focus on the transfer of current from D3, okay, D3 and D1, D3 and D1. So of course, before the zero crossing to the positive half cycle, so here we have the condition of D3 and D4 is turned on, isn't it? D3 and D4 turn on. So D3 will carry the IDC. Okay, so we have, this is the blue waveform here is actually the IDC. So this is I D3, okay, and the yellow current waveform here is actually ID1. Okay, so we observe that because of that source inductance, right, because of that source inductance, there is a overlap between those currents, ID1 and ID3. Because why? When voltage goes into the positive half cycles, the current in ID3 reduce or falls with a certain rate. It will fall, it will reduce with a certain rate until it reach zero levels. And for the ID1, it will rise with a certain rate compared to the without the source inductance just now. It changed instantaneously from 0 to IDC and from IDC to 0. But because of that source inductance, there is a overlap whereby the current in the diode doesn't change instantaneously, but there is an overlap of these two currents, which means D1 and D3 during this time are on. Both are on state. They are on state at this particular windows. So this is known as commutation interval. So this is known as commutation interval mu, or we also call it as a overlapping period, and the overlapping of periods. So during this time also, we're going to see that the supply the output voltage also goes to 0. So now let's look at what happens if this during this overlap period. Okay, so to describe, let's look into this circuit, PSIM circuits. So D1 and D3 are on, isn't it? So D1 and D3 are on. So when the diode is on, it will appear as a short circuit, isn't it? It will appear as a short circuit here. D3 also short circuit, as well as D2 and D4 also, they will be short circuit because they are also on. So if you look at this state, the equivalent circuits, or we're going to see that this point and that point will be short circuit, isn't it? Will be short circuited. So therefore, the output voltage here will be 0. Okay, so that's why we have the output voltage equals to 0 during the overlap period. So and that's why we have a 0, and therefore U also U is known as an overlap period, and the overlap angles here, or the overlap period or overlap angles here, will end when the current ID1 reach the IDC, as well as ID3 reduced to 0. So that marks the end of the overlap period, and that is denoted by the U, the angle of U overlap. So we're going to analyze what will be, do the analysis, and to find what is the equation for U. Yeah, what is the equation for U here, the overlap angle, and as well as we're going to look at the output voltage, the average of the output voltage. Okay, so first, to obtain the There is an explanation here, you can read again. Okay, while the equivalent circuit during overlapping periods will be this. Okay, so we just consider this loop, because this is short circuit, D1 is short circuit, as well as D3 short circuit, right? So we're going to look into this particular loop only, this loop, go to that loop. Okay, so we're going to consider only that loop. Right, so this is equivalent circuit during overlapping period. So you have Vs, the supply voltage, and then we have a VL, the voltage across the inductor, and this is short circuit, the diode 1 and diode 3 also short circuit. Okay, so in this case we do the KVL, take the KVL across the circuit. We're going to have Vs equals to VL, and therefore we have V peak sine omega t equals to Ls di over dt, and it is convenient to convert into radians. So we have theta equals to omega t, therefore d theta equals to omega dt. So if you replace in this equation, then you get V peak sine theta then equals to omega Ls di over d theta, because you have this differentiation, isn't it? Okay, right, and then we integrate both sides, we cross multiply the d theta here, so we have V peak sine theta d theta, so we have to integrate both sides. And now look into the current and also the angle. So for voltage, we integrate from 0 to mu, and for the current, let's look at the current. So the current is actually, during this time, the integration should be from IDC to IDC, minus IDC to IDC. Okay, so that's why you have this equation, because you integrate with respect to di, right? You integrate with respect to di, and therefore the limit should be minus IDC to IDC. Okay, right, so you solve that, and finally you found out that the angle can be determined by using this equation, right? U equals to cos inverse cos 1 minus 2 omega Ls IDC over Vp. Okay, and to obtain the average output voltage. Okay, and now we know what is a U, the mu or U, and now we're going to identify what will be derived, what will be the output voltage equation, the average of the output voltage equations. So remember, before this, without the source inductance, okay, we already derived for the voltage equation, the average voltage equation for the full wave rectifier without the source inductance. And if you compare to the voltage that we obtain with the case of with the case of the source inductance, there is actually a voltage drop, isn't it? There's a small voltage drop here. There's a small voltage drop here. Okay, so the strategy is, we know the average voltage here, then why not we just minus the average voltage here to obtain the total average voltage for your VDC in this case, isn't it? Okay, so the focus is to get the area under the curve, or the voltage drop, and then we're going to get the average voltage drop here, and then you just subtract the VDC from the without the source inductance with the small area drop here. That will give you the output voltage, the average of the output voltage. Okay, so that's what we're going to do. So go back to that. Then, okay, so to obtain the average voltage, its waveform shown in figure 4.12. So this is the average of the without the source inductance. It is observed that there is a missing area. I just explained just now. So there's a missing area during the computation angle interval. So VDC can be determined if the average voltage drop missing area is known and subtracted from the average output voltage without the LS. Okay, so again, to find the voltage drop or the area under the curve, you just simply evaluate or integrate the supply voltage here, and then you integrate from 0 to mu, isn't it? So therefore you have this, so the voltage drop, the area is 0 to u, and then you have v peak sine theta d theta. So that will give you the missing area. And we found out that equation 4.49 here actually equals to equation 4.47. So let's have a look. 4.7. So it is equals with that to this equation, isn't it? So therefore you don't have to evaluate, you just simply know that the V drop here also equals to 2 omega ls IDC. Since the output voltage repeats by pi, the average voltage drop becomes, you have to divide by pi to get the average. So therefore the voltage drop equals to, the average voltage drop becomes 2 omega ls IDC. I think I made a mistake here. This is not sorry, this is not hat, cannot be hat. Okay, this is not hat. You have to remove this hat here, because hat is actually the maximum. Okay, so you remove that. This is the average voltage. So the average voltage has to be 2 omega ls IDC over pi. Okay, so therefore finally the average load voltage will be equation 4.42. If I can click that, so this is your voltage output without the source inductance, and then you just subtract with, the average voltage drop during the overlap, which is 2 omega ls IDC. Okay, so we found out that the output voltage now becomes 2 V peak over pi minus 2 omega ls IDC. So if you want to find the average voltage drop, then you do this, get this equation. Okay, and therefore the effect, so what is the how does the source inductance affect the circuit? Is for first one is the reduction in the average output voltage, which is VDC here. So there is a reduction because of the missing area, so there is a reduction of average voltage waveform. And the other effect of having that source inductance is that there is a distortion on the voltage supply of the converter. Okay, so let's look at this circuit. So mainly, if you think of this, we have this rectifier, and then connect to your wall socket. So this is your wall socket here. If you want to connect to load 2 and load 3, so probably you want to connect to your PC, to your laptop, okay, which is load 1, load 2 and load 3, as well as you have the same point connect to your rectifier here. So because of that, we're going to see that the voltage at this point of common coupling will be distorted. So this is actually the output voltage reflect back to the input side. Sorry. So you have the output voltages now, which is we have this missing area here. So this is reflected back to the front side, the input side, and therefore the voltage supply at this point now become distorted. So this is voltage at that particular point. Okay, so therefore your load 2 and load 3 will now see a non-sinusoidal voltage supply that fit their that will be input to the load here. So there will be a problem with harmonics that we will be experienced by load 2 and load 3. Okay, so let's try to have a problem 1 here in the single phase full wave uncontrolled rectifier. So you can try to simulate, and again with the simulations you can find the U. So how to get the U from the simulation? I think I've shared with you how to get the beta from the simulation. So you just make a you just relate to U 20 millisecond, which is 50 hertz. The period for 50 hertz is 20 millisecond. So in 20 milliseconds equals to 360 degree, and therefore you must measure the delta t of u, and then you convert that into degree. So that will give you the degree of 11.04 degree, and then you can also find the average of the output voltage. Okay, so have a try, and thank you. Bye.